Welcome to Math 201. This is our lesson on section 5.2, approximating definite integrals. So let's just review. What is a definite integral? It is the area between a curve and the x-axis, but we have a little caveat that area above the x-axis is positive and area below the x-axis is negative. So our notation for a definite integral looks like this, like that elongated S from a to b of f of x dx. Okay, and it means here's a, here's b. It's the area between the curve and the x-axis between a and b. All right, we've approached our first activity for this lesson. Pause your video, try these problems. When you're ready to go over them, come back and press play. On the graph, shade the area between g of x and the x-axis. All right, so for all the parts that I can see, we've got this region. That's some area that's between g of x and the x-axis. And then I've got this region here that is between g of x and the x-axis. And then there's still a little bit more that is not as obvious, but this region here is also between the x-axis and g of x, and this region here. So for all of the graph that's drawn, that is the area between g of x and the x-axis. Let the area between g of x and the x-axis between -2 and 0 be a constant a that's positive. So the area between g of x and the x-axis between -2 and 0. So here's -2, here's 0, g of x, x-axis. So this region we're calling a. Okay, and then the area between g of x and the x-axis between 0 and 3, that's this region here, we're going to call b, which is also a positive area. Okay, that's just an area, so it's positive. Write the values of the following definite integrals in terms of a and b. So the integral from -2 to 0 of g of x dx, that is defined as the area between g of x and the x-axis between -2 and 0. Area above the x-axis is positive, so this is just a. Okay. The integral from 0 to 3 of g of x dx. So that's the area between g of x and the x-axis. But because this is below the x-axis, this is supposed to be negative when we're dealing with an integral. They told us that b is positive, so I'm going to have to take the opposite of b. Then the integral from -2 to 3. So this is all of this together. So a is positive, b is negative, and we add them together. So a plus the opposite of b. And then the integral from -2 to 3 of the absolute value of g of x. Here, that makes everything positive, so it's going to be a plus b. B was supposed to be negative in a definite integral, but if we take the absolute value, now it's positive. Approximate the integral from -2 to 3 of x squared dx using left and right hand sums with 5 subdivisions. So we'll start with left. We're going from -2 to 3. So I'm going to mark those spots on the x-axis. Then I have to break that into 5 equal pieces. So I've got 1, 2, 3, 4, 5. So 5 subdivisions, 1, 2, 3, 4, 5. And then I'm going to build rectangles over each of these intervals using a left-hand sum. So that means on the left endpoint of the rectangle, I'm going to go up to the curve and build a rectangle at that height. So left endpoint at -2, I go up to the curve, I build a rectangle at that height. I do that for each interval. And these are my rectangles that I'm going to add the area of to estimate the area under the curve from -2 to 3. We'll look at this integral from -2 to 3 of x squared dx. We are approximating this with a left-hand sum with 5 subdivisions. And now just add up the area of each of these rectangles. So the base of this rectangle is 1. The height of this rectangle is the height of the function at -2. So I can see from the graph that it's 4, right? The height of this rectangle is 4. The way I could do that without a picture is I could plug -2 into the function x squared. So I'm going to write that down. I'm going to put -2 squared. That's how you calculate the height of the function at -2. You just plug -2 into your formula x squared. Okay, my next rectangle, base is 1, and the height is the height of the function at -1. So I take my -1, plug it into x squared. Okay, my next rectangle, the height of the base is 1. The height of the rectangle is the height of the function at 0. From this picture, I can see that it's 0. From the formula, you just plug 0 into the formula x squared. And then my fourth rectangle has a base of 1, and the height is 1 squared. And my last rectangle, base of 1, and the height is 2 squared. And that comes out to 4 plus 1 plus 0 plus 1 plus 4, which is 10. Now I'm going to estimate the same integral from -2 to 3 of x squared dx with a right-hand sum, 5 subdivisions. So I'm going from -2 to 3, break it into 5 equal pieces. And over each interval, I'm going to build a rectangle. The height of that rectangle is the height of the function at the right endpoint. So we go to the right endpoint of the interval, in this case, -1. We go up to the graph and we draw a rectangle. Do that on every interval. Now I have 5 rectangles whose area I just need to add up, calculate and add together. So the first rectangle, base is 1, height looks like 1, but the way I figure out that height, not just by looking at the graph, is to plug this -1 into the function x squared. So this is 1 times -1 squared. Next rectangle, base is 1, the height is the function value at 0, so 0 squared. Next rectangle, 1 times the height of the function at 1, which is 1 squared. Next rectangle is base of 1. Height is the height of the function at the right endpoint. In this case, that's a 2. So 2 squared gives me 4. And then the last rectangle is base of 1. And then the height of the function is the height is 3 squared. Take this value of 3, plug it into the function x squared, and you get 9. And when we add that up, we have 1 plus 0 plus 1 plus 4 plus 9, which is 15. When will a sum overestimate the definite integral and when will it underestimate? Let's look at the 2 examples we just did to see if we can get some insight to answer this question. So I grabbed L5, which I drew the rectangles for, and R5, which I drew the rectangles for. I want to look at where each of these is an underestimate versus an overestimate. Okay, so when I look at left 5, these first two rectangles are overestimating the area under the curve. So right here, we have an overestimate. And then for the rest of the graph, my rectangles are underestimating the area under the curve. There's area under the curve that's not being counted. So these are an underestimate. And then when I look at right 5, it's the opposite. So these first two rectangles are an underestimate because there's area under the curve not being counted by the rectangles. And then the second part of the graph, my rectangles are counting more area. They're counting area above the curve. So it's overestimating the area under the curve. So let's see if I can summarize what it is about the function. So this function x squared is decreasing until 0, and then it's increasing. And it does sort of, the rectangles do opposite things with left and right. So I'm going to write two sentences, one for left and one for right. So left-hand sum is an overestimate when f is decreasing, and an underestimate when f is increasing. Okay, that just summarizes what we see in this picture. When f is decreasing, my left-hand sum was an overestimate. F was increasing, my left-hand sum was an underestimate. Now I'm going to summarize what I see over here with the right-hand sum. So right is an underestimate when f is decreasing, and an overestimate when f is increasing. How could we make our sums more accurate? We could use more rectangles. In fact, the definite integral from a to b of f of x dx is the limit as n goes to infinity of the left or the right-hand Riemann sum. So here's a picture of a Riemann sum. This one is actually using midpoints, but we have 1, 2, 3, 4, 5 rectangles estimating the area under this curve. And then we go to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rectangles. And you can see that there's way less error, right? The overestimate and the underestimates are like these teeny tiny little pieces of rectangle. And then when we go to like 100 rectangles, you can hardly even tell that this isn't an exact picture of the area under f of x. So if we let the number of rectangles go to infinity, you actually get the exact area under the curve. So here's the full-fledged, hardcore, no messing around definition of the definite integral. If the function f is continuous on the interval from a to b, then the way I approximate it is with a right-hand Riemann sum. So it will be the limit as n goes to infinity of the right-hand Riemann sum. So let's write out the right-hand Riemann sum. We defined it earlier, so I'm just going to write it out again. This is the limit as n goes to infinity of, okay, the right-hand Riemann sum was delta x times f of a plus delta x plus delta x times f of a plus 2 delta x plus dot 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 till we get to the very last rectangle, which is an area of delta x times f of a plus n delta x, which would be f of b. Okay, that's our right-hand Riemann sum. We're taking the limit as n goes to infinity. Okay, now each of these inputs into f, I'm just going to call these special x values. Like let's call this x1, x2, and xn, right? So I'm just taking the function value at some x values um, times f of x1 plus delta x times f of x2 plus dot 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 plus delta x times f of x sub n. Okay, and then I'm just going to write this using summation notation. So the limit as n goes to infinity, I'm going to write this Greek letter that stands for sum. And we're going to say every term in this, because this is just a great big sum, right? So a term plus more terms plus the last term. Every term in here looks identical except for the subscript on this x, which is changing. So it goes 1 and then 2 and then 3 and it goes up till n. So every single term looks like f of x with a subscript times delta x. Okay, and that subscript starts at 1 and goes until n. Starts at 1 and goes until n. So I'm going to put I equals 1 to start and stop it at n. And then we just need to say delta x. Remember, we define that as b minus a over n. And x sub I is a plus I delta x's, right? Because that's how I defined these x sub n's, a plus some delta x's. We call a and b the limits of integration, and f of x is called the integrand. We've reached our second activity for this lesson. I'm going to have you pause the video, try these problems, and when you're ready to go over them, come back and press play. Consider the function g of x equals x. We're going to compute the integral from 0 to 4 of g of x dx using limits, the limit definition of the integral. So we're going to use n subdivisions. So I need to write down the width of each subdivision. That's my delta x. And that's always b minus a over n. And in this case, my a and my b are 0 and 4. So this is going to be 4 minus 0 over n, or 4 over n. And then it says, using right-hand approximations, write down the height of the first rectangle, the second rectangle, and the third rectangle. Okay, so I'm going to draw a picture of what I'm finding the area of. So g of x equals x. So that's just a line like that. I'm going to go from 0 to 4. So I'll put 4 down here. And I'm breaking it to n equal pieces. So I'm not giving you a specific number like 5. So I'm going to have to just make small tick marks. And they just want me to write down the formulas for the first 3 rectangles. So I'm just going to put like a few tick marks um, and draw some rectangles. And I don't know how many there are because it's n. So I can't figure out exactly how many tick marks to make. So I'm just going to stop after I've drawn a handful. So I am going to use a right-hand approximation. So for each of these intervals, I'm going to go up to the curve and draw a rectangle. And I'll go ahead and do 4 of them. Okay, so I already know the width of each rectangle is 4 over n. So if I want to find the area of each of these rectangles, my base is 4 over n. But what is my height? My height is the height of the function at this endpoint. So I need to know what these x values are at each tick mark I drew. So I know that the width is 4 over n. So if I'm starting at 0, then this first tick mark is 4 over n. And then my next tick mark is going to be 4 over n plus 4 over n, which is 8 over n, and then 12 over n, and then 16 over n, right? So I'm just taking my step size is 4 over n. So now I know the base and I can figure out the height. So they just want me to write down the height of the first three rectangles. So height of the first rectangle, okay, it's going to be the height of the function at 4 over n. So it's g of 4 over n, but the function g is just g of x equals x. So the height is 4 over n. And then the second rectangle height is going to be g of 8 over n, which is 8 over n. And the height of the third rectangle is going to be g of 12 over n, which is 12 over n. And then we want to figure out the height of the kth rectangle. So like a random rectangle. Um, so I'm just going to draw a few more in here. And the height is the height of the function at the right endpoint. So my first tick mark is at 4 over n, and the second is 8 over n, and the third is 12 over n, and then 16 over n. So 4, 8, 12, 16. These are multiples of 4. 4 times 1, 4 times 2, 4 times 3, 4 times 4. My kth rectangle is going to be 4 times k. So this is going to be 4k over n. So my kth rectangle, the height is going to be g of 4k over n, which is 4k over n. Okay, use those heights we just figured out to write an estimate for the integral from 0 to 4 using right-hand approximations and n subdivisions. Okay, so my integral from 0 to 4 of g of x dx. Okay, my first rectangle, all my rectangles have a base of 4 over n. And then my first rectangle had a height of 4 over n. In my second rectangle, the base is 4 over n and the height is 8 over n. Third rectangle is 4 over n and the base is 12 over n. And I'm going to keep going until I get to the last rectangle, which is going to have a base of 4 over n. And the height is going to be the height of the rectangle at 4. But we have broken our interval up into n pieces. So I'm going to write that as 4n over n. And I should have written this as approximate. Okay, so this ends up being 16 over n squared plus 32 over n squared plus 48 over n squared plus dot 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 plus 16n over n squared. And if I want to write this in summation notation, I have to think about what these terms all have in common. They all have an n squared. Okay, so I'm going to write a big summation formula. And then I have to write each term, think about how each term looks the same. They all have an n squared on the bottom. Okay. And then my numerators are multiples of 16. This is 16 times 1, 16 times 2, 16 times 3, up until 16 times n. So they're all 16 times something. And that something starts at 1 and goes until n. All right, let's compute the value of the right-hand Riemann sum. Okay, so we're going to use this useful fact that if you're adding up the first k integers, there's a shortcut for that. It's k times k plus 1 over 2. All right, so I'm working on the integral from 0 to 4 of x dx. And this was approximated by the sum from I equals 1 to n of 16i over n squared. And then to expand that, that means 16 over n squared plus 32 over n squared plus 48 over n squared plus dot 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 plus 16n over n squared. Okay, I am going to factor out I have a bunch of terms here. I can factor out 16 over n squared. And what's left here is 1 plus 2 plus 3 up to n. Okay, and this sum has a formula. K times k plus 1 over 2. I'm using n, so it's going to be n times n plus 1 over 2. So this is 16 over n squared times n plus 1 over 2, which is 16 over n squared times n squared plus n over 2. That's going to reduce. And then I have 8n squared plus 8n over n squared. And then that can be broken up into two fractions, 8n squared over n squared plus 8n over n squared. And that simplifies to 8 plus 8 over n. Okay, finally, I'm going to take a limit as n goes to infinity. So just to recap, I'm trying to figure out the integral from 0 to 4 of x dx. I said, okay, well, that can be approximated by the sum from I equals 1 to n of 16I over n squared. And we just did a bunch of work on the previous page to say that that equals 8 plus 8 over n. Okay, and then this was just an approximate sign when I was doing a Riemann sum. Okay, but if I let the number of rectangles go to infinity, and I put in the limit as n goes to infinity at each step, eight over n goes to 0, and this just becomes 8. Okay, how do I know this is right? I could draw a quick picture of f of x equals x. I want the integral from 0 to 4. That's just a triangle. This is 4 by 4. So the area is 1/2 times 4, which is 8. For our last example, we're going to set up an estimate for the integral from 0 to 1 of h of x dx, where h of x equals x squared. So if we're using n subdivisions, the width of each subdivision, which we call delta x, is going to be the full length of the interval from 0 to 1, so 1 minus 0 over n, which is just 1 over n. Okay, if we're going to use left-hand approximations, we want to write down the height of the first rectangle, the second rectangle, and the third rectangle, and I'm going to draw a picture. So I'm looking at x squared from 0 to 1. Something like that. Okay, so I'm going to make some tick marks. I don't know exactly how wide to make them. I'm just making them small-ish because I need to put n of them. I didn't give you a specific number, so I'm just going to draw a few. And I know that my delta x, the width of each interval, is 1 over n. So this is going to be 1 over n, 2 over n, 3 over n, 4 over n, etc. Each step is 1 over n. So height of the first rectangle is going to be g of 0. Okay, because my first interval is right here, and they said that we're using a left-hand approximation this time. So the height is the height of the function at the left endpoint, so g of 0, which is 0 squared or 0. Okay, and then the second rectangle is going to be g of 1 over n will be its height. So you go up to the graph at 1 over n, make the rectangle, and that height is going to be 1 over n squared, which is just 1 over n squared. And then the third rectangle is going to be g of 2 over n, which is going to be 4 over n squared. If I just draw a few more tick marks, and I'm going to call one of them the kth rectangle. So this is the first, second, third, fourth. This is going to be the kth rectangle. So this right endpoint is k. So this is k over n. But the height of the rectangle is at the left endpoint. So I need k minus 1 over n. So the kth rectangle is going to be g of k minus 1 over n, which is k minus 1 squared over n squared. Now use the above to write an estimate for the integral from 0 to 1 of h of x dx using left-hand approximations and n sigma subdivisions using sigma notation. But we're not going to evaluate this sum. Okay, so we're just going to say the integral from 0 to 1 of x squared dx can be approximated by a sum of rectangles. Okay, so the first rectangle's height was 0. So its width or its base was 1 over n, and its height is 0. Okay, my second rectangle, its base was 1 over n, and its height was 1 over n squared. And the third rectangle, base was 1 over n, the height was 4 over n squared. Okay, and then my next one would be 1 over n times 9 over n squared. And I keep going until I get to the last rectangle, which is 1 over n times n minus 1 squared over n squared. And if I want to write this in sigma notation, I would look at all of these terms and say, okay, what do they have in common? They all have a 1 over n as the first factor. So it's going to be 1 over n times something. Okay, and the something is going to be, maybe instead of writing this as 0 squared, I might put that as 0 over n squared instead of just 0. So this is 0 over n squared, 1 over n squared, 4 over n squared, 9 over n squared. So this is, these are the perfect square numbers, 0, 1, 4, 9, up to n minus 1. So they are perfect square numbers. We'll call them I minus 1 squared over n squared. And I is starting at 1 and going to n.